All right, welcome to Recitation 4 from MAE 242, Intro to Fluid Mechanics. Today we're going to talk about forces on curved surfaces and stuff like that. So it's my understanding that a lot of you guys already have a little bit of a background in the subject, so that'll be nice. Shouldn't have to go into all that much depth. But at any rate, so here's our first problem. Now I'll explain a little bit more as I go. But to start off, okay, so this is the first problem we're going to be tackling. We want to find an analytic formula for the vertical and horizontal forces on each semicircular panel AB. I denoted right there. The width end of the page is B. Which force is larger and why? All right. So first off, we want to find the vertical and horizontal force. So what I always do first, I always think it's way easier to find the horizontal force first. So over here, you can start drawing over here, right? So FH, the horizontal force. We want to, for all of this stuff, for force on curved surfaces, we always think about the horizontally projected area, right? So if you're looking at both of these tanks, right, if you look at them from the side, and I always say this, imagine you're looking at a staircase with one eye closed, right? It just looks like a wall, just like a rectangle, right? Just a rectangular wall. You don't know if it's going up or down or whatever. Same thing for water. If you're water, looking at this curved surface right here, you don't know that you're looking at anything curved. You just know you're pushing up against something, right? And however that force vector ends up being, whatever, right? But as far as when we're calculating the overall horizontal force, we just worry about that projected area. And in this case, since it's a semicircle, it's just a rectangle, right? So now, from there, it's literally the exact same steps as you did for any other object. Once we start taking the horizontal projected area, it's back to the same. So FH, pressure at the centroid, right, times the projected area. So let's keep going. So FH equals, what's our pressure at the centroid? It's rho G HC. And now what's our projected area? It's that diameter times the width of the page. Cool? So let's do this one more time. You get FH equals rho G. What's the height of our centroid? It's H plus D over 2. Now times D times B. All right. And as you can see, this thing we get right here, this is the same for both. Okay. Cool. And that might, it feels weird at first, but if you think about it, like what I just explained, it's just the horizontal projected area, right? It doesn't matter, that right there, that's horizontal projected area. And then this right here is the same horizontal projected area. It's the same surface the water is pushing up against, that it thinks it's pushing up against, right? Quote unquote, thinks. So it's really cool. That tracks. Anybody having questions with that something really mind blowing to you guys? Or is that pretty easy? Pretty cool. Yeah, I'll just math it out. It's not too bad. But now, all right, let's move to the vertical. Okay. So that's all good and well, but let's move to the vertical, right? For FV, we care about volume. All right, we care about the volume of the water. In this case, it's like, you want to be a little bit careful when you refer to volume, okay? I'll show you what I mean. A lot of times, it just depends on what, reference you're talking about. But at any rate, the general formula is FV equals rho G times V. Some volume of water, some volume of thing being displaced, whatever. It's just the weight of the water, right? Weight of the water, or weight of the water being displaced, whatever, who cares? So let's start mathing this out. And this is where things get kind of convoluted, all right? Because essentially what you end up doing, okay? Let's look at this one on the left. Call this tank 1, right? So, for any sort of pressure scenario that we get going, we're going to have all these pressure vectors pushing down here, and as we go down, right, so we get something something like this going. We got everything's always acting perpendicular to the surface. All right, but as we get down here, these force vectors start pushing upwards, right? And if as you've taken all of this fluid class stuff, as you go deeper down, pressure increases, and therefore the force of pressure increases. So from the jump, if you're talking about, okay, how's this vertical force going to be acting? The forces down below are going to be pushing up a little bit harder than forces up top are pushing down because they're deeper down below, right? And it's pushing on the same sort of curved surface, right? So there's going to be some sort of net force pushing up. All right, so now how do we go about doing that? So this is really what you end up doing. Okay, let me redraw this real fast. We've got our thing here. And I'm only going to draw this once because once I prove this, you just do the same thing in reverse for this one over here. And I just notate that on there. So anyway, what you end up doing, you end up taking this whole volume up here, right? This entire thing, right? You take that and I just minus this, but you don't care about that. But anyway, so you end up taking that and you end up subtracting this whole bit out from up here. Because like I said, the force pushing down, right? You're going to have some, I'll call this F upper, and then some force down here, call it F lower, right? You're going to have those two different force vectors pushing on each other. But like we said, intuitively, you just know there's going to have to be some net force pushing up, right? You're going to have some like F net equals FL minus F upper. And what this turns out to be, and like we just said before, these forces up here are just rho g times volume of the water or whatever. And in this case, you care about this whole volume too. So the lower is the volume of this entire thing. And so you end up subtracting this upper bit. And so what you're left with is just the volume of this semicircle right here. So you end up being left with, which is rho times g times half of a circle, 5, 4 times space, the volume of that thing. All right. Does that make sense, everyone? Just in this case, the volume you're worrying about is the volume being displaced, right? That's why I say be careful with what you mean by volume, but sometimes it's kind of misleading. So that's what this equals here. All right. And now same thing for this one up here, right? So this is for tank 1. It's funny, look how much better my handwriting is when I'm like nice and careful, I'm like writing it down. It'll be presented. Then when I'm on the fly, so same thing for this bit right here, except we don't care about this little bottom quarter right here because nothing's going on there, air right there. What you end up doing here is taking this whole volume, subtracting this whole volume out, right? And so you get the volume of this thing right here. So same thing for tank 2. But, right, FV for 1, right, is acting upward. Because, like I just said, you've got this net force pushing up because force vectors down here are stronger, right? And opposite's true for 2. Right? Because it's just the opposite thing. You get these force vectors, way more force pushing down here to a little deeper, right? But in the grand scheme of things, look at what what this stuff's telling you, right? Look at all this stuff. This is independent, or at least for for the vertical force. It's pretty independent of the actual depth the thing is underneath whatever body of water it is, right? This right here is the whole hinging moment for buoyancy, which is what we'll talk about here in a second. Have you guys talked about buoyancy at all? All right, buoys and things and how stuff floats. So this is the main thing you got to worry about for buoyancy, independent of the actual depth of the object under the water, which we want about improve. And it ends up just being some function of volume. So purely geometric. All right, everybody cool with that? Oh, it's just the depth of the page, which yes, oh, yeah. So yeah, the width, or you usually see it like W. So, all right, any other questions? Cool. All right. So like I said, a little teaser. Let's move on to question 2, which is all about this. And yeah, have you guys talked about buoyancy at all? You guys have no idea what buoyancy is. Yeah. That's fine. Get after. So for this one, we have a 7 diameter aluminum ball with specific gravity of 2.7 and a brass ball with specific gravity 8.5 are attached to a pulley and balanced nicely when submerged. A, if fluid is water, and I already gave you the before it, find the diameter of the brass ball, dBr. The diameter of brass ball is 3.8 centimeters. Find the density of fluid. So A and B are like independent of each other. All right. So once you find stuff for A, don't go back to the B. That's it. But anyway, so from the jump, we've got a pulley system, and we got some buoyancy stuff going on. So you're gonna have to draw a free body diagram. All right. The step 0 when you see like forces and stuff. So let's start with the aluminum ball. Right. So we've got sucker here, and we have some weight pushing down, the weight of it pulling itself down. And it's attached to a pulley, so we got some tension force. You go, well, all right, well, wait a second. This would be really, really easy. All right, there's got to be some trick to it. And you're right, there's a trick to it. Because, like we were saying, there's always some buoyant force pushing up on whatever, if anything is ever sitting in a fluid, even air, like there's a buoyant force acting on us from air. You just don't feel it because air is not dense at all. But yeah, when you've done a cannonball into a pool, like hold the basketball and you launch the thing up, that's buoyancy at people's MA. Buoyancy is a force. So anyway, I'll show you how you go about doing this in a sec. But for now, let's just write our equations, right? Like our sum of moments in the y, the 0. So we got t pointing up minus w plus fb. We'll also substitute around because we're dealing with some sort of tension force, so let's just solve for tension right away. You're gonna have to figure it out some way. You're gonna have to go over to the brass one. We get t plus w minus fb. And w is easy enough. W of aluminum is rho g times the volume, which in this case I've written down. Got after you multiply, 2.7 times 998, you get 2694.6 kilograms per cubic meter times 1.81 times volume of a sphere, 4/3 pi r cubed. And in this case, I'm just going to go 0.07 cubed over 8. Right, so plug that in. The weight of the aluminum ball is about 4.747 newtons. All right, cool. So now we go, all right, so still don't know anything about the tension or the buoyant force. This is when you go on your exam, you open up your cheat sheet, right? You open up your little note sheet, and go, oh yeah, there's just a nice little equation for buoyant force. So FB equals the density of the fluid times gravity times the volume being displaced by some object in that fluid, okay? Very important. Volume being displaced. And I say that very, very sternly because it just so happens in this problem that the volume being displaced by both of these is just the total volume of the ball because they're both fully submerged. But you can imagine a scenario where, let's say this ball is floating up top in here, and the water level only goes like halfway, right? Obviously, the displaced volume now is just half of the circle or half of the sphere, whatever. So it so happened in this problem, they were nice to us and gave us total volume, which is called thing. So whatever, go plug in those numbers. You get FB equals 998 times 1.81 times same thing, 4/3 pi r2. FB equals 1.75. All right, cool. So now equals 4.767. Our tension force is 2.989. All right, so I'll move like, I'm not even gonna draw another free body diagram for the brass one. You guys know, just end up drawing another free body diagram for the brass one. Same thing, you get the same governing equation, T equals W minus FB. So go. But now we don't know the diameter for either. But the same tension force, we go 989 equals rho BR G times third I BR cubed over 8 minus right. And so for the sake of time, I'm kind of lazy. You guys can put this stuff in. We know the density of bronze, right? You just multiply it. No, I will. No. So let's go plug everything in. All right, so we get 2.989 equals, what's the density of bronze? Multiply 8.5 times 998. We get 8483 times 9.81. And yes, I realize you can like factor out a gravity thermometer times 4/3 by the 8. All right, now from here, obviously, just expand that out. You get something in terms of d cubed, that draft of d cubed, draft those two, move it over, take the cube root of it, solve for d. Getting d is 7 meters equal to 4.27. All right. Everybody cool with that? Not too bad. Pretty chill. This buoyancy equation, just straight up equation. She'll go through like a proof of it. If you haven't already. Yeah, take my word for it. That's buoyancy equation. Rho g times the volume being displaced, volume of fluid being displaced by whatever object pushing up. Always acting up, upward. So we'll move to part B. Any questions with that? So for part B, you're just basically doing the same thing, but in reverse. Would be what, 3.8. And so there's a couple ways to do this. I think the PDF that we'll post along with this has this done in like one step, but I'm gonna show you how to do it my way because I'm able to learn both ways. So again, I'm not going to redraw the three Bode diagrams. We're still going to be using the straight up the T equals W minus FB situation here. But if you notice in this one, it's going to be a little harder because we'll never know the tension force because we'll never know buoyancy force because we don't know density of the liquid, right? But that's fine. So let's keep going. So for aluminum, right, we have T equals W minus FB. T equals the weight is, I will do 2694.6. Now minus some rho fluid that we don't know. Cool. And you go, okay, I don't know T, I don't know rho FL. So that's fine. Move on to brass. Move on to the other one. Again, T just equals W minus FB, as we saw before. We go T equals 84, 83. So now they gave us the actual diameter for it. So, all right. So now again, we don't know rho FL, we don't know T. But hey, that's fine. 2x2 system. Two equations, two unknowns, right? Right? And so in this case, this makes it really easy because we have T equals that. So I'll just take this equation, plug it in up there. Now you have one equation, one unknown. Really easy. Now this I'm not going to go and do algebra for. It's just typing numbers on a calculator. I assume you guys can all do that. So after solving, it's left as an exercise to the reader. You got the density of this unknown fluid equal to 1592 kilograms per cubic meter. Which that makes sense. I always love harping on like doing a little sanity check at the end of this stuff. This makes sense. The density of this unknown fluid higher than the density of water, which is fine because as you saw up here, we solved for 4.27 centimeters with this ball in water. And so we said for part B, we're going to make that smaller. We're going to make it 3.8 centimeters. So for everything to still balance while this aluminum ball is still 7 centimeters, the water or the fluid it's being immersed in has to be a little denser. We have to push it up, push the smaller ball up a little harder, so they have to balance with the other guy. Cool? Sweet. All right. Anything else anybody wants to know about this bad boy or the other one? We're chilling. Okay. But yeah, just be very careful with, I explicitly said FB is, the displaced volume, the volume of the fluid being displaced. Is that pretty important? I would probably say on a homework, you might see something where like, some object isn't fully submerged or like only 3/4 of it is. So don't get caught out doing that. Usually for like the scope of exam, we'll probably try and make it pretty easy for you. Just show us the concept and it's cool. But just know your stuff. Get your stuff down. What's up?
For the diameter of sorry, for the area, volume of a sphere, is that just a formula where it's like that, the 4/3?
Yeah, 4/3 power cube.
Okay.
Just
And then is it always going to be over 8? Or
Oh no, I just did that because it's 4/3 pi radius cubed, and but we're given a diameter, so I just know it's the diameter cubed.
over 8?
Yeah, over 2 cubed. That's so just diameter cubed 8. Okay. I could just put like 2 to 3. I know what 2 to 3 is. 8. So anyway, cool. All right. There's no further questions. I'll call that good there. I'll stop the recording.